Hello everyone, welcome to our channel Knowledge of. Friends, subscribe to our channel and click the bell icon for the latest update. Today we're gonna start with your chemistry class, and that is your class 12. This is your class 5, where we had completed your 4 classes of chemistry, and that where we had discussed unit 1, that is your the solid state. The second unit we have your solution. As you can see, this surely will complete here. In the last topic, what in the last class what we had talked about it, which we had discussed the last topic as well, which is depressions of freezing point, elevations and point as well, and that we had discussed the last is a model boiling point, elevations and freezing point depression constant for the sum solvent. Now with reference towards that, we'll start with the question here itself. First of all, it's a huge request to all of you to please go through with the subscribe button. Please like, share and subscribe our channel so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. Now we will be going ahead with the first question of the session here, and that is the 9th question of this unit. So that we are solving. The question is 45 gram of ethylene glycol, which is C2H6O2, is mixed with 600 gram of water. Calculate the freezing point depressions and the freezing point of the solution. So let's go ahead with that. 45 gram of ethylene glycol, C2H6O2 is mixed with 600 gram of water. Calculate. What we have to calculate? The first you'll calculate the freezing depression. And the second we have to calculate is your freezing point of the solution. So with this we'll go ahead. That's what we have to talk about it. Here the preparation in a freezing point is related to the molality. Therefore, the molality of the solution with respect to the ethylene glycol, we have molality equals to moles of ethylene glycol. In terms of ethylene glycol we are talking about, we are finding the molality as well, upon mass of water in kilogram. So moles of ethylene glycol we have equals to 45 gram upon 62 gram mole inverse, which is equals to 0.73 mole. Mass of water in kg equals to 600 gram upon 1000 gram kg inverse. So where this 0 is cancelled by this one with this, so this is 10 is in the denominator, it will put after the one digit that will put the decimal, so that is 1 kg here. That inverse comes upside and become positive. So hence molality of ethylene glycol equals to 0.73 mole upon 0.60 kg that we have here 1.2 mole kg inverse. Therefore the freezing point depression equals to, which is delta TF equals to 1.86 kg mole inverse into 1.2 mole kg inverse is equals to 2.2 K here. Freezing point of the aqueous solution equals to 273.15 K minus 2.2 K, that is equals to 270.95 K. Now we will be doing the 10th question of the session, and that what we have to discuss as well. And here we go ahead with the 10th question of the session as that what we have to discuss in this class. The question 10th we have. The question is 1.00, which is 1 gram of non-electrolyte solute dissolved in 50 gram of benzene, lowered the freezing point of benzene by 0.40 K. Freezing point depression constants of benzene is 5.12 kg mole inverse. Find the molar mass of the solute as well. So let's go ahead. 1.00 gram of a non-electrolyte solute dissolved in 50 gram of benzene lowered the freezing point of benzene by 0.40 K. The freezing point depression constant of benzene is 5.12 kg mole inverse. Find the molar mass of the solute. So that what we have to solve it out. So in the same case for here, and that what we have to go ahead with substituting the values of the various terms involved in this, and that we'll get here, which is your M2 equals to 5.12 kg mole inverse into 1.00 gram into 1000 gram kg inverse upon 0.40 into 50 gram, and that is equals to 256 gram mole inverse. So the molar mass of the solute equals to 256 gram mole inverse. Now we will go ahead with the discussion about the another topic which we have to discuss here, and that is the osmosis and osmotic pressure. Osmosis and osmotic pressure. So we are in the same case that what we have to go ahead and even though that what we have to discuss here in a same pattern that we will discuss. So there are many phenomena which can be observed in nature or at home. For example, raw mangoes shrivel when pickled in a brine, which is a salt solution water. That is wilted a flower that revive when placed in fresh water, and blood cells collapse when suspended in a that is saline water, etc. If we look at these processes, we'll find one thing common in all. That is, all these substances are bound by the membranes. These membranes can be of animal or vegetable origin, and these occurs naturally, such as pig's bladders or the parchments, or that can be synthetic such as cellophane, and that is these membranes appears to be the continuous sheet of films, and yet they contain a network of submicroscopic holes or poles as well, where in the same cases here that small solvent molecules like water that can pass through these holes, but the passage of bigger molecules like solute is hindered. Membranes having the kind of properties are known as semi-permeable membrane, which is known as that is SPM here. In the same cases that assume that only solvent molecules can pass through these semi-permeable membrane. If this membrane is placed between the solvent and solution, solvent molecules will flow through the membrane from a pure solvent to the solution, and this process of flow of the solvent is called osmosis. The flow will continue till the equilibrium is attained, and the flow of the solvent from the side of the solution side across the semi-permeable membrane that can be stopped if some extra pressure is applied on the solution. This pressure that just stops the flow of solvent is called osmotic pressure of the solution, and the flow of the solvent from dilute solution to the concentrated solution across a semi-permeable membrane is due to the osmosis. And the important point that to be kept in mind is that the solvent molecule always flows from lower concentration to the higher concentration of solution. The osmotic pressure has been found to depend on the concentration of the solution as well. The osmotic pressure of the solution is the excess pressure that must be applied to a solution to prevent osmosis, that is, to stop the passage of solvent molecules through the semi-permeable membrane into the solution, and that is the osmotic pressure is an colligative property as it depends on numbers of solute molecules and not on their identity. For a dilute solution, it has been found that experimentally that osmotic pressure is proportional to the molarity, and that C of the solution is the given temperature T we have, and that we talk about it, and that we have where here this one is the osmotic pressure, and this R is the gas constant here, and with the same cases it will be written as N2 by V RT, and that is here the V is the volume of the solutions in liters that containing the N2 moles of solute, and where the W2 gram of solute of molar masses, and M2 is present in the solution, then N2 equals to, where we can say that N2 equals to W2 by M2, and that we can write it down as well here. And in the same cases that we have to go ahead, which that is V equals to W2 RT upon M2, or we can say that M2 equals to W2 RT upon V. This is what we have when we are finding out M2 here. Now with this, now knowing the quantities W2, T, this and V, and that we calculated as molar masses of the solute, here the measurement of the osmotic pressure that provides another matter of determining the molar mass of solute, and this method is widely used in determining molar masses of proteins, polymers, and of course with reference towards it that the other that macro or molecules, and the osmotic pressures method that have an advantages over the other method, as pressures measurement is around the room temperature and the molarity of the solution is used instead of molality. As compared to the other colligative property, its magnitude is large even or very dilute solution. The technique of the osmotic pressure for the determination of molar masses of the solutes is particularly useful for the biomolecules, as they are generally not stable at higher temperature and polymers have poor solubility as well. In the same cases where the two solutions having the same osmotic pressure at a given temperature are called isotonic solution, and when such solutions are separated by semi-permeable membrane, no osmosis occurs between them. And for example, the osmotic pressures associated with the fluid inside the blood cell is equivalent to that of 0.9% mass per volume, and sodium chloride solution that called normal saline solution, and it is safe to inject intravenously. On the other hand, if we place the cells in solutions containing more than 0.9% mass per volume, the sodium chloride where water will flow out of the cells and they would shrink, and such a solution is called hypertonic. And if the salt concentration is less than 0.9% mass per volume, the solution is said to be hypotonic, and in this case water will flow into the cells if placed in the solution and they would swell here. Now we will be going ahead with the question here, that what we have to talk about it, and that is the 11th question of the session here. So I tell you about the question here, which is 200 centimeter cube of an aqueous solution of a protein contain 1.26 gram of protein. The osmotic pressure of the solution at 300 Kelvin is found to be 2.57 into 10 to the power minus 3 bar. Calculate the molar mass of the protein, that what we have to talk about it. And let's go ahead with the question as well. With other question, that is your 11th question of the sessions here. Let's go ahead with that. 200 centimeter cube of an aqueous solution of a protein contains 1.26 gram of the protein. The osmotic pressure of such a solution at 300 Kelvin is found, that is to be 2.57 into 10 to the power minus 3 bar. Calculate the molar mass of the protein. Let's go ahead with the solution for this. The various quantities known to us that we have equals to 2.57 into 10 to the power minus 3 bar. V equals to 200 centimeter cube, which is equals to 2.200 liter. T equals to 300 Kelvin, and R equals to 0.083 liter bar, mole inverse and Kelvin inverse. Substituting these value here, what we'll get? M2 equals to 1.26 gram into 0.083 liter bar, Kelvin inverse, mole inverse, into 300 K upon 2.57 into 10 to the power minus 3 bar. into 0.200 liter, and that is equals to 61.022 gram mole inverse. This will be the right answer for this question as well. With the same case, the phenomena that mentioned in the beginning, and that's what we had discussed here on the basis of osmosis. Raw mangoes placed in a concentrated salt solution loses water by the osmosis and shrivels into the pickle here, and that is wilted flowers revive when placed in fresh water. A carrot that has become a limb because of water loss into the atmosphere that can be placed into the water, making it firm once again. Water will move into them through osmosis, and when placed in water containing less than 0.9% mass per volume salt, and that is your with references towards it, that the blood cells that collapse to the loss of water by osmosis, and people taking a lot of salt or salty food experience water retentions in tissues, cells here, and intercellular spaces because of osmosis, and the resulting that we have here, which is view, that is what we have to talk about it, that the resulting puffiness of or swelling is called edema. Water movement from soil into the plant roots and subsequently into the upper portions of the plant is partially that partly due to the osmosis, and the preservations of meat by salting and of fruits by adding sugar protects against bacterial actions, and through the process of osmosis, a bacterium on salted meat, or a candid fruit loses water and that shrivels and dies as well. Now we'll go ahead with other topic that what we have to discuss here, which is in the terms of reverse osmosis and water purification. Reverse osmosis and water so that what we have to talk about it. In the directions of osmosis that can be reversed if the pressure is larger than the osmotic pressure is applied to the solution side, and that is now the pure solvent flows out of the solution through the semi-permeable membrane. This phenomena is called reverse osmosis and is of great practical utility. Reverse osmosis is used in desalinations of seawater, and a systematic setup for the process that we have. And when a pressure more than osmotic pressure is applied, pure water is squeezed out of the seawater and through the membrane. A variety of the polymer membranes are available for this purpose as well. Where in the same case, that is the pressures required for the reverse osmosis is quite high, and a workable porous membrane is a fill of cellulose acetate placed over the suitable support, and that the cellulose acetate is permeable to water but impermeable to impurities and ions that present in seawater. And these days many countries uses desalination plants to meet their potable water requirement as well, where one side is the salt, and then we'll piston through piston we are pushing the pressure here, and that the pressure will equal to that, and that the pure outlet that the fresh water it will give it out, that the water outlets as well. Now we'll go ahead with the sum of the unsolved question that I had told you about it, and that is the solved question. We are dealing with 11th question, and the unsolved question that I have given you 8 question I had given you in this related to this chapter. The 9th question we have the vapor pressure of a pure water at 298 Kelvin in 23.8 mmHg, 550 gram of urea, which is NH3CONH3, is dissolved in 850 gram of water. Calculate the vapor pressures of water for this solution at its relative lowering as well. This is the 9th question. The 10th question that you have to do by your own side, that is boiling point of water at 750 mmHg is 99.63 degrees Celsius, and how much sucrose is to be added to 500 gram of water such that it boils at 100 degrees Celsius. The 11th question we have, which is to calculate the mass of ascorbic acid, vitamin C, which is C6H8 and O6, that we have, and that to be dissolved in 75 gram of acetic acid to lower its melting point by 1.5 degrees Celsius, where Kf is equals to 3.9 K, that Kelvin kg mole inverse. The other we'll talk about the 12th question of the session here. Calculate the osmotic pressures in pascals exerted by solution prepared by dissolving 1 gram of polymer of molar mass here. That is of molar masses that is being 185 1,85,000 in 450 ml of water at 37 degrees Celsius. So these were the fourth question, and that we had arrived at 12 questions here. Now we will just talk about the another question here, another topic, which is abnormal molar masses. In terms of abnormal molar masses here, we know that the ionic components, when dissolved in water, that dissociate in the cations and anions. And for example, if we dissolve 1 mole of KCl 74.5 gram in water, we expect 1 mole each of K plus and Cl minus ions that to be released in the solution. And if this happens, there would be the 2 moles of particles in the solution, and if we ignore the antirenuric attraction, 1 mole of KCl in 1 kg of water, that would be expected, and to increase the boiling point by 2 into 10 to the 0.52 Kelvin equals to 1.04 Kelvin. So now if we did not know about the degree here, and that is in the same cases that to dissociation, we could be led to conclude that the mass of the 2 moles that we have, the 2 moles of particles, is 74.5 gram, that mole here, and the mass of 1 mole of KCl, that would be 37.25 gram. And it brings into the light that the rule that when there is dissociations of solute, that solute into the ions, and the experimentally determined molar mass is always lower lower than that true value as well. So where we can see that here the equation for this, 2CH3COOH, it will give CH3COOH equal to twice. For this we have a structure as well, HOCCH3 double bonded O, HO CH3. So for that here, and that is the molecules of ethanoic acid, acetic acid, that is your dimerizes the benzene due to the hydrogen bonding, and they normally happen solvent in the low dielectric constant, and in this case the numbers of particles is reduced due to the dimerization. An association molecule is depicted here as follows. Well, it can be undoubtedly stated here that if all the molecules of ethanoic acid associates in benzene, then the delta Tb or delta Tf for the ethanoic acid will be of the normal value, and the molar mass calculated on the basis of the delta Ti, that will be therefore the twice the expected value, and such the molar masses that is either lower or higher than the expected or a normal value is called as abnormal molar masses. In 1880, that Van 't Hoff introduced a factor I known as a Van's factor, and to account the extent of dissociation, association factor I, that is defined here as follows, which is I equals to normal molar mass upon abnormal molar mass, that is equals to observed colligative property upon calculated colligative property, which is equals to total number of moles of particles after association or dissociation number of moles of particles before association or dissociation. Here, the abnormal molar mass is experimentally described that determined the molar mass and calculated the colligative property that are obtained by the assume that the non-volatile solute is neither associated nor dissociated, and that in the case of the association the value of I is less than the unity, and while the dissociation is greater than unity. So for example, the value of I for the aqueous that KCl solution is close to 2, and while the value for the ethanoic acid in benzene nearly 0.5. Inclusions of 1/2 factor modifies the equations for the colligative property, that is relative lowering of the vapor pressures of solvent, and that we have P1 naught minus P1 upon P1 naught equals to I N2 upon N1. So here elevations of boiling point, if I am talking about, elevation of boiling point delta TB equals to I kbm, where depression of freezing point delta TF equals to I kfm, osmotic pressure of solution equals to I N2 RT upon V. So here for that that I for the several strong electrolytes for the KCl, NaCl and MgSO4, I approach to as the solution becomes very dilute, and as expected the value of I that get close to 3 for K2SO4, and in the same case the values of 1/2 factor I at various concentrations for NaCl, KCl, MgSO4 and K2SO4. For that we have here, we'll talk about the salt, which is values of I 0.1 m, 0.01 m and 0.001 m. Then we have here 1/2 factor I for complete dissociations of solute. So the first salt we have NaCl, then another we have KCl, MgSO4 and K2SO4. For the NaCl 0.1 m, that is your 1.87, 0.01 m, that is 1.94, 0.00 m, that is 1.97, and the van 't Hoff factor are for a complete dissociations of solute we have 2.00. For KCl we have 1.85, 1.94, 1.98, and this is 2.00. For MgSO4 1.21, 1.53, 1.82, and this is 2.00. This is K2SO4 for 2.32, 2.70, and 2.84, so that is 3.00 as well that we have, and that is that I values representing for the incomplete dissociations here. Now we'll go ahead with other one that what we have to discuss here, which is the another question that what we have to discuss. And the question we have, that is 2 gram of benzoic acid, which is C6H5COOH here, dissolved in 25 gram of benzene, shows the depressions in freezing point, and that equals to 1.62 K. Molar depression constant for the benzene is 4.9 K kg mole inverse. What is the percentage association of solid if it forms a dimer in solution? So let's go ahead to do it. That is the 12th question of the session here. Two gram of benzoic acid, C6H3, so H5COOH, dissolved in 25 gram of benzene, shows a depression in freezing point equal to 1.62 Kelvin. Molar depression constant for benzene is 4.9 K kg mole inverse. What is the percentage association of acid if it forms dimer in solution? So let's go ahead with this question here. The solution for this, which is in the same case the given quantities are that we have W2 equals to, that is your 2 gram, Kf equals to 4.9 kg mole inverse, and W1 equals to 25 gram, and delta Tf is equals to 1.62 K. Substituting these values here, we will get M2 equals to 4.9 kg mole inverse into 2 gram into 1000 gram kg inverse upon 25 gram into 1.62 K, which is equals to 241.98 gram mole inverse. For thus, the experimental molar mass of benzoic acid in benzene is equals to 241.98 gram mole inverse. And now consider the following equilibrium for the acid, which we have 2C6H5COOH. It is C6H5COOH whole twice. If X represents the degree of the association of solute, then we would have 1 minus X mole of benzoic acid that is left in unassociated form, and corresponding X by 2 as associated moles of benzoic acid at equilibrium. So therefore the total number of moles of a particular at equilibrium that we have is your 1 minus X plus X by 2 equals to 1 minus X by 2, and thus the total number of moles of particles at equilibrium equals Van't Hoff factor I, but I equals to normal molar mass upon abnormal molar mass. And in the same cases we'll go ahead further, and that will put the value, which is 122 gram mole inverse upon 241.98 gram mole inverse that we have, where in the same case or X by 2 is equals to 1 minus 122 upon 241.98, which is equals to 1 minus 0.504, which is equals to 0.496. So or we can say that X equals to 2 into 0.496 and we'll multiply 0.992. So here that is, therefore the degree of association of benzoic acid is of benzene is 99.2%. Now we'll go ahead with other question that what we have to talk about it, which is your the 13 question and the solved question, that is your last question of the session that we are dealing with the solved here, and that we have 0.6 ml of acetic acid, which is CH3COOH, having density of 1.06 gram milliliter inverse, is dissolved in 1 liter of water, and the depression in freezing point observed in 1 liter of water. The depressions of freezing point observed for this strength of acid was 0.0205 degrees Celsius, and calculate the Van't Hoff factor and the dissociation constants of acid as well, that what we have to go ahead. So for that sake we have that the 13th question here. The question we have 0.6 ml of acetic acid CH3COOH having density 1.06 gram milliliter inverse, is dissolved in 1 liter of water. The depression in freezing point observed for this strength of acid was 0.0205 degrees Celsius. Calculate the Wand's half factor and the dissociation constant of acid. That we have to talk about it, and here that the number of moles of acetic acid of acetic acid equals to 0.6 ml into 1.06 gram milliliter inverse upon 60. So here on the same cases we go ahead, which is 60 gram mole inverse equals to 0.0106 mole here, that is equals to N. Molality equals to 0.0106 mole upon 1000 ml into 1 gram ml inverse equals to 0.0106 mole kg inverse. Using this equation we have delta TF equals to 1.86 kg mole inverse into 0.0106 mole kg inverse equals to 0.0197 K, where Wand's of factor which is I equals to observed freezing point upon calculated freezing point, that is equals to 0.0205 K upon 0.0197 K equals to 1.041. Acetic acid is a weak electrolyte and will dissociate into two ions, acetate and hydrogen ions, per molecule of acetic acid. If X is the degree of the dissociation of acetic acid, then we would have N1 minus X of moles of undissociated acetic acid, NX moles of CH3COOH minus, and NX moles of H plus ion, where that is equals to, for the CH3COOH, if I am talking about, for that the N mole, that is H plus is 0 and CH3COO minus will be 0, and 1 minus X for that, and X mole for H plus 1 and an X mole for SCH3COO minus as well. So the total moles of the particles we have N 1 minus X, that is plus X and plus X, only X, that is equals to N 1 plus X, plus minus and plus cancel, so it will be 1 plus X. So for that I equals to N 1 plus X upon N, this N and M cancel, that is 1 plus X, which is equals to 1.041. Thus the degree of association of acetic acid is here, which is X equals to 1.041 minus 1.000, that is equals to 0.041. And for then CH3, if I'm talking about the CH3COOH, and that is CH3COOH minus here on the same basis, so that we have here CH3COOH, which is N here, that is 1 minus X, and it is equal to 0.0106 1 minus 0.041 for CH3COOH minus, which is equals to NX equals to 0.0106 into 0.041 equals to into H plus equals to NX, and that is equals to, we have, which is equals to here, that is NX, that is equals to 0.0106 into 0.041. For that, K of A equals to CH3COO minus, and this is H plus upon CH3COOH, it is equals to 0.0106 into 0.041 into 0.0106 into 0.041 upon 0.0106 1.00 minus 0.041, and that is equals to 1.86 into 10 to the power minus 5 here. Now in the same case that what we have to talk about, there are many questions as well. With the first, starting with that, we have to start with the discussion about the summary here. And in the same case where that a solution is a homogeneous mixtures of two or more substances, where solution that is classified as solid, liquid and gaseous solution. The concentration of a solution is expressed in the terms of mole fraction, molality and in percentage, and that the dissociations of a gases in a liquid is governed by the Henry's law, according to which at a given temperature the solubility of a gas in a liquid is directly proportional to the partial pressure of a gas, and the vapor pressures of the solvent is lowered by the presence of a non-volatile solute in the solution, and this lowering of vapor pressures of the solvent is governed by the Raoult's law, according to which the relative lowering of the vapor pressures of the solvent over the solution is equals to the mole fractions of the non-volatile solute present in the solution. And however, in a binary liquid solution, if both the component of the solutions are volatile, then the another form of the Raoult's law is used. Mathematically, this form of the Raoult's law is stated as where P total is equals to P1 naught x plus P2 naught x, and that is x2. The solutions which are obeys Raoult's law over the entire range of concentrations that are called ideal solution. The two types of deviations from the that is the Raoult's laws, called the positive and negative deviations, are observed, and azeotropies arise due to the very large deviations from the Raoult's law as well. The properties of the solution which depends on the numbers of the solute particles and are independent of their chemical identity and are called colligative property. These are lowering of vapor pressures, elevations of boiling point, depressions of freezing point, and osmotic pressure. The process of osmosis that can be reversed if the pressure is higher than the osmotic pressure is applied to the solution, and colligative properties have been used to determine the molar mass of the solutes. The solutes which dissociates in solutions exhibit the molar mass lower than the actual molar mass, and those which associate the show higher molar mass than their actual molar values as well. Quantitatively, the extent to which a solute is dissociated or associated, that can be expressed by the Van-Hoff law factor, and that is the factor has been defined as the ratio of the normal molar mass to experimentally determined molar mass, or as the ratio of observed colligative property to the calculated colligative property as well. Now we will be going ahead to discuss about the another one which we have to discuss here. In the reference towards it, there are the many questions that what we have to discuss here. That is the another question is that to define the term solutions, how many types of solutions are formed, write briefly about each type with an example. The another question we have is you give an example of solid solutions in which the solute is a gas. Another is define the following terms where the mole fractions, molality, molarity, mass percentage. Another question, concentrated nitric acid that is used in the laboratory worked in 68% nitric acid biomass in aqueous solution, and what should be the molarity or in such samples of the acid if the density of the solution is 1.504 gram milliliter inverse as well. In the same case, the another question is a solution of glucose in water and is labeled as 10% W by W. What would be its molality and mole fractions of each component in the solution, and if the density solution is 1.2 gram mole in milliliter inverse, and what shall be the molarity of the solution? How many ml of 0.1 m that mole of HCl are required to react completely with a 1 gram of mixtures of Na2CO3 and NaHCO3 containing the equimolar amounts of both as well? That what we have to discuss here, which is we have to discuss the another question here. So on the same cases, the another question we have, a solution is obtained by moving 300 gram of 25% solution and 400 gram of 40% of the solution by mass. You have to calculate the mass percent of the resulting solution. The other question is that the antifreeze solution is prepared from 222.6 gram of ethylene glycol, which is C2H6 and O2 here, and that are 200 gram of water. That calculate the molality of the solution, and if the density of the solution is 1.072 gram milliliter inverse, and then what shall be that molarity of the solution here. Now where a sample of drinking water was found to be severely contaminated with a chloroform, which is CaCl3, supposed to be that is your carcinogen, and the level of the contaminations was 15 ppm by mass, and that we have to express this in the percent by mass and to determine the molality of that chloroform in the water sample as well. The other question is the 10th question here, other one, which is what role does the molecular interfaces that interactions plays in a solutions of alcohol and water. The other question is why do gases always tends to be the less soluble in liquid as the temperature is raised. The another 12th question is the states Henry's laws and mentions some important application. The other question is that the partial pressures of ethane over the solution containing 6.56 into 10 to the power minus 3 gram of ethane is 1 bar, and if the solution contains 5 that is 0.00 into 10 to the power minus 2 gram of ethane, then what shall be the partial pressures of the gases. And the other question is what is meant by positive and negative deviations from the Raoult's law, and how the sign of delta max min h that is related to the positive and negative deviation from the Raoult's law. The another question is an aqueous solutions of 2% non-volatile solute exerts a pressures of 1.004 bar at the normal boiling point of the solvent, and what is the molar mass of the solute here. The another question is that we have is your heptane and octane form an ideal solution, and at 373 Kelvin the vapor pressures of the two liquid components are 105.2 kPa and that is 46.8 kPa respectively. What will be the vapor pressure of a mixtures of 26.0 gram of heptane and 35 gram of octane as well? The another question that has been arises that the vapor pressures of water is 12.3 kPa at 300 K and Kelvin, that is, and calculate the vapor pressures of 1 mole solution of a non-volatile solute in it. And the other question is to calculate the mass of a non-volatile solute, which is molar mass 40 gram mole inverse, which should be dissolved in 114 gram octane to reduce to its vapor pressures to 80%. A solution containing 30 gram of non-volatile solute exactly in 90 gram of water has has a vapor pressures of 2.8 kPa at 298 Kelvin, and further 18 gram of water is then added to the solutions and the new vapor pressure become 2.9 kPa at 298 Kelvin, and calculate its molar mass of the solute and vapor pressure of the water at 298 K here. The another is a 5% solution biomass of a cane sugar in water has freezing point of 271 Kelvin. Calculate the freezing point of 5% glucose in water if freezing point of pure water is 273.15 Kelvin here. The another is that that is the element A and B form the compounds having the formula that we have is the AB2 and AB4, and when dissolved in 20 gram of benzene, which is C6S6, 1 gram of AB2 lowers the freezing point by 2.3 Kelvin, and whereas 1.0 gram of AB2 here, AB4, that lowers it by 1.3 Kelvin, and the molar that depression constant for benzene is 5.1 Kelvin kg mole inverse as well, and in the same case to calculate the atomic mass of A and B here. Now we're going ahead with the discussion about the another question, which is at 300 in Kelvin, the 36 gram of glucose present in a liter of its solution has an osmotic pressures of 4.98 bar, and if the osmotic pressures of the solution is 1.52 bars at the same temperature, what would be the what would be its concentration? That what we have to talk about it. The another question is that to suggest the most important type of the intermolecular attractive interactions in the following pairs, which is N-hexane, N-octane, I2, NCCl4, NaClO4 and water, methanol and acetone, and that is your acetonitrate, which is CH3CN, and acetone, which is C3H6O here. The another question is based on the solute-solvent interactions, arrange the following in order of increasing solubility in N-octane and explain cyclohexane, KCl, CH3OH and CH3CN as well. The another question is amongst the following compound identify which are insoluble, partially soluble and highly soluble in water, which is phenol and toluene, that is formic acid, ethylene glycol, chloroform and pentanol. The another question is that is if the density of the Sam Lake water is 1.25 gram milliliter inverse and contain 92 gram of Na plus ions per kg of water, calculate the molality of Na plus ions in the lake. The another is if the solubility product of CuS is 6 into 10 to the power minus 16, calculate the maximum molarity of the CuS in aqueous solution. The another we have is you calculate the mass percent of the aspirin, which is C9H8O4 in that acetonitride, and CH3CN, which is when 6.5 gram of C9H8 and O4 is dissolved in 450 gram of CH3CN here. Now we will be talking about the another question here, which is the naphthalene 6 C19H21NO3, similar to the morphine, is used to combat withdrawal that symptoms in the narcotic users. Dose of the nalorphine is generally given in 1.5 mg, and you have to calculate the mass of 1.5 till 110 to the power 3 m aqueous solution required for the above dose here. The another question is to calculate the amount of the benzoic acid, which is C6H3COOH, that is required for preparing a 250 ml of 0.15 m solutions in methanol. The another is the depressions in freezing point of water observed for the same amount of the acetic acid, which is trichloroacetic acid and a trifluoroacetic acid, increases in the order given below. We are explained briefly. The another is to calculate the depressions in the freezing point of the water when 10 gram of CH3, CH2, CHCl, COOH is added to 250 gram of water, where that is your Ka is equals to 1.4 into 10 to the power minus 3, Kf equals to 1.8386 kg mole inverse. The another question is 19.5 gram of CH2 FCOOH is dissolved in 500 gram of water. The depressions in the freezing point of the water observed in 1 degree Celsius. Calculate the Van Hoff factor and dissociation constant of acetic acid. The another is the vapor pressures of water at 293 Kelvin in 17.535 mmHg. Calculate the vapor pressures of water at 293 Kelvin when the 25 gram of solution glucose is dissolved in 450 gram of water here. The another question is that the Henry's law constant for the molality of the methane in benzene at 298 Kelvin in 4. That is 4.27 into 10 to the power 5 mmHg. Calculate the solubility of methane in benzene at 298 Kelvin under the 760 mmHg. The another question is 100 gram of liquid A, which is molar mass 140 gram mole inverse, was dissolved in 1000 gram of liquid B, molar mass of 180 gram mole inverse. The vapor pressures of pure liquid B was found to be the 500 torr, and calculate the vapor pressures of pure liquid A and its vapor pressures in the solution if the total vapor pressure of the solution is 475 torr here. Now we'll go ahead with other question that what we have to talk about it, which is the vapor pressures of a pure acetone and a chloroform at 328 K are 741.8 Hg and 632.8 mmHg respectively. Assuming that they form an ideal solvent over the entire range of composition, we have plot P total and P chloroform and P acetone and the functions of X methane. The experimental data observe the different components of mixtures here. That you have to plot the data also to the same graph paper, and then you have to indicate whether it is provide the deviations of negative deviations from the ideal gas or not. The other question we have to find out is to benzene and toluene form the ideal solution over the entire range of composition. The vapor pressures of the pure benzene and toluene is at 300 Kelvin at 50.71 mm and 32.08 mmHg respectively, and calculate the mole fractions of benzene in a visible phase if 80 gram of benzene is mixed with 100 gram of toluene here. The another question we have that the air is a mixture of a number of gases. The major components of that oxygen and nitrogen with approximate proportions of 20% and is to 79% by volume at K, and that is the water is in the equilibrium with its at pressure of 10 atm at 298 Kelvin. If Henry's law constants for oxygens and nitrogens at 298 Kelvin are 3.30 into 10 to the power 7 mmHg, and then on the same basis we have, which is your 6.51 into 10 to the power 7 mm respectively, you have to calculate the composition of these gases in water. The another question we have, the 40th question that we had discussed here itself in these question. This is 40 question. We approximately, if I'm talking about, so here we had discussed about 70 to 80 questions here with including the solved question as well as the unsolved questions inside the topic, and as well as the after the topic as well. The other question is the 40th question in the same cases, that to determine the amount of CaCl2, and that is I equals to 2.47, that dissolve in 2.5 liter of water, and that is the osmotic pressure is 0.75 atm at 27 degrees Celsius. The another 41 question we have, that to determine the osmotic pressures of a solution prepared by dissolving the 25 mm, that is K2SO4 in 2 liter of water at 25 degrees Celsius, and assuming that it is completely dissociative, that we will end up here. So this is the other questions here. So here we'll end up with, and in the next coming class we'll start with the another unit, which is unit 3rd, which is electrochemistry here. So in this chemistry, other than the chemistry, we are dealing with the quantitative aptitude, where we had covered up the 18th classes here, and other than that we are dealing with the that we had completed the sociology, and we are dealing with the software engineering as well. And other than that as well, we are dealing with the reasoning, where we had completed the verbal reasoning, that has been including the general mental ability, and as well as the logic reasoning, which we had completed. In the non-verbal reasoning, that we are dealing with a series where we had done that the more than 1000 questions, and in analogy we are dealing with the 500 question. The the another topic we are dealing with, that is your the classification, and hopefully in the next coming 2 classes will end up with that as well, and we had started with that as well. So in this same cases, if in talking about the chemistry for the class 12 there, which is also important for the competition wise as well, because this has been including the NCERT here. In terms of it, unit 1, that we had completed the solid state, where we had covered up the general characteristics of solid state, amorphous and crystalline solids, classification of crystalline solids, crystal lattice and unit cells, numbers of atoms in the unit cells, closed pack structure, packing efficiency, calculation involving the unit cell dimensions, imperfections in solids, electrical properties, magnetical properties as well. In terms of unit 2, that is your solution, where we had completed the types of solution, expressing the concentration of solution, solubility, vapor pressures of liquid solution, ideal and non-ideal solution, colligative property, and determinations of molar masses, as well as the abnormal molar masses as well. In terms of unit 3rd, if I'm talking about, that is your electrochemical chemistry, which is where we had discussed about the electrochemical cells, galvanic cells, Nernst equation, conductance of electrolytic solution, electrolytic cells and electrolytes, and batteries as well. In the other cases, we are dealing with a fuel cells, as well as we'll discuss about that is your that the correlation as well in the next coming class, which is of unit 3rd, electrochemistry. After that, we will discuss the unit 4, which is your chemical kinetics. In that, we have to discuss the rate of the chemical reactions, factor influencing the rate of reaction, integrated rule equation, pseudo first order reaction, temperature dependence of the rate of the reaction, collision theory of the chemical reaction. In unit 5th, which is your surface chemistry, where we have to discuss the adsorptions, catalysts, colloids, classification of colloids, emulsion, colloids around us. In unit 6, which will have to discuss the general principles and process of isolations of element, where that we have to discuss the occurrence of metals, concentrations of ores, extractions of crude metal from a concentrated ore, and then we have to discuss the thermodynamic principles of metallurgy, electrochemical principles of metallurgy, oxidation, reduction, refining, uses of aluminium, copper, zinc, and iron as well. The other, we have to discuss the p block element, where we have to discuss the group 15 element, dinitrogen and ammonia, oxides of nitrogen, nitric acid, phosphorus, allotropic forms, phosphine and phosphorus halides, and that is oxo acids of the phosphorus as well. Group 16 element, dioxygen, and that is your the simple oxides, ozone, sulfur, allotropic forms, sulfur dioxide, oxo acids of the sulfur, sulfuric acid. Group 17 elements, chlorine, hydrogen, chloride, oxo acids of halogens, that is enter-halogen compounds, and group 18 elements as well. The other unit 8, we have to discuss the D and the F block element, where we have to discuss the positions in the periodic table, electronic configurations of the D block element, general properties of the transition element of D block, some important compounds of transition element, the lanthanoids, the actinoids, and some applications of D and F block element as well. Other than that, we have to deal with the another unit, which is your the unit 9, that is we have to discuss the coordination compound, and that we have to discuss the Werner's theory of the coordination compound, definitions of some important terms pertaining to the coordination compound, nomenclatures of coordination compound, isomerism in the coordination compound, bonding in the coordination compound, bonding in metal carbonaceous, and that stability of the coordination compound, importance and implications of coordination compound as well. So here we'll end up with, and we'll start with the unit 3rd in the next coming class, which is your the electrochemistry here. It's a huge request from my side to all the viewers. Please go through with the subscribe button and please like, share and subscribe our channel so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. And these were all the subjects which are important towards your side, so please go through with the subscribe button and please like, share and subscribe our channel. And whatever the topic, whatever the subject you want from our side, you can just comment on, and we will surely provide you soon as well. So thank you, hope you enjoy this video. If you like this video, please give a thumbs up and give a suggestion on the comment box. Thank you.